Okay, I want to illustrate the process by which we can use power series to solve a differential equation. And I want to take a look at a differential equation we've been able to solve since the beginning of the semester. Y prime minus y equals 0, or dy dx or dy dt minus y equals 0. Let's have t as our independent variable there. We know how to solve this. If y prime equals y, we're looking for a function which is its own derivative. You solve this without knowing any techniques at all, practically on the first day. We know that a function which is its own derivative is e to the t, or e to the x, if x was our independent variable, or any multiple of that. Let's go ahead and take a look at how we could do this using series, just to illustrate the idea. So let's let y of t be a series. We'll give it a power series. So a0 plus a1t plus a2t squared plus a3t cubed plus a4t to the fourth plus, and so on forever. We said a power series is like a polynomial, but it doesn't have a finite degree. It goes on forever. You can think of it like an infinite degree polynomial. Let's go ahead now, since the differential equation is a first order differential equation, we're going to need to take the derivative. So derivative of a constant is 0. Derivative of a number times t is just the number. Derivative of a number times t squared, the 2 comes down, a2t. The next term, if we take the derivative, will be 3a3t squared. If we take the derivative of the next term, we have 4a4t cubed, plus, and so on. Again, we can take, under conditions that you would have studied in a Calculus 2 class, but I'm going to just take for granted here, the derivative of a Taylor series, a power series, term by term. Let's go ahead and plug these things into the differential equation. So y prime is a1 plus 2a2t plus 3a3t squared plus 4a4t cubed, plus dot dot dot. If you don't like the plus dot dot dot, feel free to use sigma notation, but I think right now this is probably the clearest way to do this, and hopefully I've left enough room on the blackboard. Plus my y, which is a0 plus a1 t plus a2t squared plus a3t cubed plus dot 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 equals 0. Let's collect up like terms. So our constant term, oh, sorry, this should be a minus sign, because we had a minus sign here. So all we did is put in y prime here in this set of parentheses, and we put in y right there in the original differential equation. Let's go ahead and collect up like terms. We have a1 minus a0 plus 2a2 minus a1 times t. Once we collect up like terms right here, and then we have 3a3 minus a2t squared, and we have 4a4 minus a3t cubed, plus, and so on. Now look what's on the right side of the equation. 0. We can think of this as a power series. We can think of that as 0 plus 0t plus 0t squared plus 0t cubed and so on. The idea being that if the two sides of the equation are equal, then that has to be 0. And that has to be 0. And that has to be 0. Because if these two power series, the one on the right side being a very trivial power series, are equal, then all the coefficients have to be equal. So we have a series of equations here. We have that a1 equals a0 and 2a2 equals a1. Because if that's 0, then a1 equals a0. We can move it on to the other side of the equation. If 2a2 minus a1 is equal to 0, then 2a2 equals a1. And 3a3 equals a2. And 4a4 equals a3, and so on. So we can solve, let me let you look at that for a second. Oh, I guess you could just pause the video when you want to look at something a little bit longer. Bet you wish you had that power in class sometimes. We can solve for all of these coefficients in terms of a0. You can see that a1 just equals a0. That's what we wrote here. So if 2a2 equals a1 and a1 is a0, we know that 2a2 equals a0, a2 equals a0 divided by 2. And if 3a3 equals a2, so then we know that a3 equals a2 over 3. And since a2 is just a0 over 2, this equals a0 over 6. a2 is just a0 over 2. Putting that over 3, we end up with a0 over 6. You end up with a4 equals a3 over 4. In other words, it's a0 over 24. I trust you recognize these numbers that are coming up. This is just a0 over 1 factorial. This is a0 over 2 factorial. This is a0 over 3 factorial. This is a0 over 4 factorial. And so on. And so, y of t is just going to be a0 plus a0 over 1 factorial t plus a0 over 2 factorial t squared plus a0 over 3 factorial t cubed plus a0 over 4 factorial t to the 4th plus and so on. And let's factor out the a0. We end up with 1 plus t over 1 factorial plus t squared over 2 factorial plus t cubed over 3 factorial plus t to the 4th over 4 factorial plus and so on. And here we actually have an answer. If you want it in simpler form, remember I asked you to memorize this power series. That's just e to the t. So this is just a naught times e to the t, a constant times e to the t, and we knew that that was the solution to this differential equation. There will be times where you'll work out a power series, at least the first few terms, and you won't recognize it. It won't be the power series of any familiar function, and maybe it isn't the power series of any familiar function. Maybe it has nothing to do with whether or not you recognize it or not. But at least you have a power series solution, and you can use this when you don't know how to solve this in closed form. When we say a naught e to the t, we have closed form. A series solution, as you can see, is not as elegant. But you can, if you need to, find the value of the function at some point, at least you could just go ahead and plug in t and take as many terms as you need to get whatever degree of accuracy you want. This is the method. At least you can get this far, and sometimes you can go back and write it this far.